I'd like to welcome all the sites who are tied in this afternoon to the Arctic Climate Modeling Program lecture series. We're privileged to have John Lingus as one of our presenters today. John is a meteorologist with the National Weather Service in Fairbanks and has worked there since 1980. He earned his Bachelor's of Science degree from Oregon State University in 1980. Along with his regular job duties, John also provides tours of the National Weather Service Forecast Office to school groups, as well as making presentations inside the school classrooms here in town. John also participates in Geophysical Institute-led education outreach programs for middle school students, such as a science and math enrichment program that some of you are familiar with. So let's give our attention to John Lingus as he speaks to us about the pressure systems. Take it away, John.
Well, good afternoon, everyone. And my talk today is on understanding atmospheric pressure systems. As we go through this time, I'm going to be posing some questions that you can feel free to answer among yourselves, each in your own classroom. I'll give a little bit of a pause, but we won't be waiting for any comments back over the phone system. I'll just give the answer after a few moments. And if there's further questions about those questions or anything else, then we have that time at the end of this talk for questions. So let's go on and let's get started. Why do we want to understand pressure systems? Well, for one thing, they help create the weather we experience. And their effect is changed by the local area we live in. Pressure charts are help us to see about weather in various places, so we get to see these through like newspapers, television, internet, a variety of places we can see these weather charts. So what is air pressure? Well, air is made up of molecules. The molecules move rapidly. They move at nearly 1,100 miles an hour. Is anybody out there move at 1,100 miles an hour? Probably not, at least on their own. The molecules bouncing off objects cause the pressure. And this is just a little stick figure of, and the red lines are what could be air molecules. These are so small we can't see them. We seldom feel pressure because our bodies adjust to the force of the air around us. But one exception that we know about is flying in an airplane. When you go up or down, we have to move our jaw to allow the pressure in our ears to become equal to the changing pressure outside. That's why sometimes people like to chew gum as they go up or down in an airplane. And air pressure is basically the weight of all the air over a certain location. Air pressure changes as you go up and down. Does air pressure increase or does it decrease when you go up in the atmosphere? And the answer is air pressure decreases when you go up. Okay, how about this question? Does air pressure decrease or increase when you go down in the atmosphere? The answer to that is air pressure increases when you go down. So when you go from a hill down to sea level, you're going to encounter increasing atmospheric pressure. So the other question is why? Why does air pressure decrease going up? Why does it increase going down? Well, the reason is that the Earth's gravity holds more air closer to the ground, thus the pressure is greater near the ground. So if you measure pressure as you move across an area or region, oftentimes you will find that the pressure is changing. The pressure also changes with time at any one place because pressure systems move. Well, to track all these changes, we talked about changing going up and down, talked about changing going across an area, we talked about changing in time. We need to measure the air pressure. And how we do this? Well, this is one way, or the main way is we use a barometer, and this is just a simple diagram of a mercury barometer. So what you have is a glass tube filled with mercury, and at the very top of the tube there is a vacuum here, so there's no air at all. And this is the liquid mercury here, and this edge here is exposed to the air on each side, so the air pressure is pushing down on the liquid and causing it to go up into the tube a certain amount of distance. So now I have a picture of two mercury barometers, one with a different amount of mercury in between the two. So which barometer is measuring the higher pressure? If you chose barometer A, that would be correct. There's more pressure, and it's causing the mercury to rise higher in the tube than in barometer B. Another way, or another type of barometer we can use, is an aneroid barometer. Well, what does the word aneroid mean? Aneroid means without liquid. And this is an important type of barometer because it's really in common use today. It's easier to use, and it's much safer than a mercury one. The mercury ones are very fragile, and mercury itself can be a dangerous chemical if you come into contact with it. So they've designed and developed some years ago this aneroid type of barometer. It uses a metal alloy strip inside a cell with very little air in the cell, so that the strip responds quite a bit to small differences in the pressure. And what kind of units do we measure the pressure in? Well, there's pounds per square inch. This is often used in man-made devices that produce pressure. For instance, like a tire pump, or maybe a fancy pump that you use to blow up sports balls. There's often, these will report the pressure in pounds per square inch. Inches is another way to refer to the pressure, and this is often used in the mercury barometers, and the aneroid barometers have adopted the inch type readings as well. Millibars is another way to measure the pressure, or to talk about how high or low the pressure is. And a millibar is 1/1000th of a bar. And you may ask, what's a bar? Well, meteorologists have used this for a long time, this type of measurement, and it comes from the Greek word baros, which means weight. So it's a 1/1000th of or 1/1000th of a bar is a millibar. Now, pressure lines. When we have various pressure measurements across an area, we can draw lines to understand how the pressure systems are changing. Because remember, one of the aspects I talked about is pressure varies across space, and another aspect I talked about was that pressure varies with time. So how pressure changes is very important to figuring out weather. A line of equal pressure, or where pressure is all the same, exactly the same at various locations, you can draw a line along those points, and that would be an isobar. And we call it an isobar because iso means the same value, and bar, again, as we just heard, means pressure or weight. So a pressure chart with lines of equal pressure looks a lot like a topographic map where there's lines for equal elevation. So here's a topographic map, actually north of Nome. I took a picture of one. And when we look at a topographic map where a stream flows, we often call that a valley. We have a hill where the elevation is the highest, and we have a hill over here where the elevation is also high. The valley is between the two hills. Where the hill is kind of extended, we have this feature called a ridge. And where the elevation is lower and kind of flat, like where this lake is, In the pressure map, there's a lot of similar features. The hills we would call highs. The ridge is the same word. We would call a ridge of high pressure extending out from a high center. Between the two ridges, in the lower elevations or the lower pressures, we would call that a trough. And in the lowest elevations, we would call that low pressure. So here's an example of a surface pressure chart. Do you see where there is a low pressure center? Where would that be located? If you said over here by the Canada coast, where this red L is, that would be a right answer, a correct one. If you said over here by the Western Aleutians, where this red low is, that would also be a correct answer. Where do you think a high pressure center is located? Well, if you pointed up here to this blue high, that would be the correct answer. Some other factors about weather system or pressure systems. For one thing, pressure systems are often huge. They can cover lots of area. This is just a weather map from a number of days ago, taken from the National Weather Service's TV weather page. And there's a low here in Bristol Bay. And the area that it's influencing is quite large here. You can see it covers much of Alaska and the North Pacific and out over the Bering Sea just from this one low pressure center. And the low pressure center isn't even all that strong, but it still has quite a wide-reaching effect. Another factor about pressure systems is they grow and they shrink over time. For instance, today there might be a small low pressure center, maybe near you or maybe some other location. A couple days later, this low pressure center may be quite expansive. It might cover a very, very large area. And then 3 days after that, this low pressure center may have shrunk or dissipated altogether. Pressure systems are also three-dimensional. So even though we can see low pressure at the ground or measure it, oftentimes there's low pressure as well above the low or slightly back to the west of the low at upper levels. Well, let's talk about the molecules involved in low and high pressures. The differences in temperature across an area causes the molecules to move. And this movement creates areas of high pressure where more molecules are present and areas of low pressure where there's less molecules. So the atmosphere is always trying to make things equal between the low pressure and the high pressure. To do that, the air flows between pressure systems. Here's a high pressure on the left and a low pressure on the right. What direction will the air move between the high and the low? Think about that for a moment. Well, if you said that the air would flow from the high pressure to the low pressure, you'd be correct. What do you think we call this movement of air molecules from high pressure to low pressure, or just the plain movement of air molecules? Well, wind is what we typically call this. So when you feel the wind, you can tell that there's a movement of air molecules from high pressure to low pressure. Let's talk about how the wind moves around the pressure systems. It's not quite true that the wind flows directly from high to low pressure. Actually, the Earth rotating around on its axis creates a force of its own that causes the wind to move to the right. So these yellow arrows depict how the wind would be flowing between high and low pressure. But in essence, what happens is that the air turns a bit to the right, about 90 degrees, and so there's a difference in the flow that results. And that's just for the northern hemisphere. If you were down in the southern hemisphere, the wind would be moving to the left. And that's okay, this type of relationship, when you're talking about airflow above the ground or in the upper atmosphere. The air would flow clockwise around a high, and it would flow counterclockwise around a low. But near the Earth's surface, another force acts on the wind called friction, and this turns the wind back to the left a bit. So, if we look at the center image here with the low pressure, the wind would flow slightly into the low pressure center as it tries to move counterclockwise around the low. Now let's talk about wind speed. Wind speed can vary in several ways. The mountains near you can block the wind, making it weaker than the overall wind the pressure systems would create. Sometimes we see this at Nome when there's moderate north winds. Nome is kind of shielded a lot from the moderate north winds. When the winds get strong enough, however, some of the strong winds hit Nome in spurts. So the winds to the north, or the hills to the north of Nome, are no longer blocking the winds as effectively as they did with somewhat lighter winds. But mountains or coastline can also enhance the wind, like through a pass, making it stronger. Some examples are Unalakleet with east winds. They tend to blow extra strong when the pressure is, when there's high pressure east of Unalakleet and lower pressure out in the Bering Sea. Gullivan, Topkok, Koyukuk, these places can blow quite strong in north winds, even stronger than what the difference between the high and low pressure would indicate. Gambell is another example, especially with regards to the coastline of the Chukotsk Peninsula to the northwest of Gambell, and then the island itself creates kind of a funnel so that northeast winds tend to blow quite strong. Wind speeds also vary around pressure systems. That's why these pressure lines or isobars are really important. And how the pressure lines are situated between each other can indicate whether the winds are fast or slow. When the pressure lines are close together, wind speeds are fast, like this top example. But when the pressure lines are far apart, wind speeds are slow. And that's shown in the bottom example. So here's a chart with pressure lines. Where do you think the strong winds are? One area that's especially favorable for strong winds is over western Alaska. And there's a few other places too I can point out. There seems to be fairly strong winds around this low pressure center. We go all the way over near British Columbia. There seems to be some fairly strong winds around the south side of this low pressure center as well. But this is the largest area here where this occlusion or weather front is moving up north over western Alaska. Where are the weak winds located at? Well, one area that's especially evident for weak winds is right around here over eastern Alaska. There's a large space between each pressure line here, and so the winds are quite light. Now let's talk about the real nitty-gritty stuff, like what type of weather comes with pressure systems. It can vary with between the pressure systems, and it often depends on the time of year. For instance, low pressure produces some clouds, precipitation like rain, snow, freezing rain, windy conditions, and thunderstorms, just to name a few of these. High pressure can have clear or decreasing clouds. And by the clouds getting smaller there, I'm indicating that the cloud cover is shrinking. High pressure is often think of sunshine, at least during the summer months. Usually means warmer temperatures, at least in inland areas during the summer. But in the winter, it can mean colder temperatures. So it does depend on the season. Sometimes high pressure can produce windy conditions, especially when it's first moving into an area. High pressure can also be responsible for fog in inland areas in the spring or autumn. And I don't know if you can see this last item about fog, but high pressure is also responsible for fog along a lot of coastal locations during the summertime. Well, just take a look here at pressure systems and the winter weather. For instance, this area, shaded area, is all the clouds that are forecast to occur or are occurring. So the unshaded areas is where there's no clouds or very little clouds to speak of. The green shaded areas are where precipitation is occurring. Up here in the eastern Arctic, there's snow. Also some snow or snow showers down here over south central or southeast Alaska. This system out in the Bering Sea is producing, a wide variety of types of precip. Snow in the north, snow showers way out to the west, some rain, even freezing rain, some blowing snow here in the various windy places. All kinds of weathers going on from this winter system that's moved into the Bering Sea. For summer, there's more daylight, as we all know. So this is what happens. The land heats up faster and it stays warmer longer than it does over the ocean. So the land gets warmer. Well, that causes lower pressure to develop over the land areas because there's warmer temperatures means the molecules are moving somewhat faster and they rise a bit. Warmer air can rise some. So near the surface there's lower pressure inland. Out over the ocean stays cooler than the land. As you know, if you apply heat to something solid like a piece of metal or a piece of brick, for instance, versus trying to warm up a pot of water, the same amount of heat, you know that the water will take longer to heat up than the brick will. So the oceans warm up a lot slower than the land does, and thus they are cooler than the land. So the oceans tend to have high pressure over them during the summertime. And what that causes is oftentimes a lot of fog along the coast or offshore especially, and sometimes on the coast if the winds are favorable for bringing those low clouds into the coastal areas. And this is what we see often over the Bering Strait, St. Lawrence Island, and at times during the summer even over Norton Sound. And that's all.
Who supplies the weather maps that we see, like on aviation weather, or when we see a news channel in the lower 48? Do you work together, or does one person take credit in each state?
Well, it comes from a variety of sources. On aviation weather, or Alaska weather, those charts are prepared by a Weather Service staff each day. And then for instance, the Aviation Weather Unit in Anchorage also provides some weather charts. The National Center in Washington, D.C., the National Center with the Weather Service, provides surface charts, surface pressure and analysis charts for the North Pacific as well. And then private meteorological companies can also supply their own weather charts for the same times for their customers. So you can get weather charts, surface pressure or pressure charts for the upper atmosphere from a variety of sources. The National Weather Service is one source, but there are other sources as well. Because, going back to that question I was just asked about the sharing of data, well, I talked about surface data being shared. It also goes for the upper air data, which is done twice a day. So everybody has access to this data. And so government agencies as well as private meteorological firms can pull in this data and create their own weather charts.
So when you're talking about private companies, they're using your data, or do they have instruments for their own use?
They're usually using, to a large part, the data that we supply or through partnerships that we get the information from. They may also have some of their own weather stations, although they're usually much fewer in number than the partnership that the Weather Service has with, for instance, not only ourselves but the FAA and then other government agencies or various state agencies as well.
When you're talking about building the charts, are you talking about a group of weathermen like yourself working together, or is it something that one person takes responsibility for?
The answer is yes. It depends on the office. In each weather office, there may be whoever's on duty at the time may want to draw a pressure chart of his or her own doing and just use it locally in their own office to understand how the pressure systems are affecting the weather in their area. The National Center in Washington, D.C. has a team of people working on various pressure charts for across the northern hemisphere at least, and so that takes several people who are doing those analysis to get them done on time every 6 hours.
When you're looking at the pressure system, what are you looking for, say, a winter storm that you have to warn ahead of time? And how much time do you have to warn a village or a coastal section?
Good question. If we go back to like that, some of those charts I showed before, especially that latter one where it showed all kinds of weather moving up western Alaska, that was a chart actually for today, which some of you out there in various places, St. Lawrence Island, southern Norton Sound, even Nome and Wales and Teller may already be experiencing a little more weather than you had the day before. But it really depends on how we understand the weather systems from day to day and how, see, all this data goes back to computer models back in Washington, D.C., where they worked through mathematical equations to make predictions about the atmosphere. Well, sometimes those computer models have similar solutions. There's a set out of Washington, D.C., actually 3 or 4 different models. There's one from a European center. The Canadians have a weather forecasting model. And the Navy has one. All different types of places have these weather models that are run on computers. And we are able to look at some of these models in the forecast office. Sometimes those models are really in close agreement, and they show a low in one location today, and 48 hours later it's about in the same location, maybe in the center of the Bering Strait at a certain depth, and the forecaster can have a lot of confidence in the weather that will come about with that system, and they may feel very confident in producing and writing out winter storm warnings or blizzard warnings, high wind warnings, whatever, for areas of western Alaska, maybe 36 hours to almost 48 hours in advance. Now, sometimes the various models have a lot of differences on what will happen with the weather system, especially when it comes from areas where there's a lot of, or there's not very much data. The data that we get across the planet and across the northern hemisphere is not evenly spaced. It just depends on where there's communities that have weather stations. So if the data comes from, if the weather system comes from a data sparse area like northern Russia or the Arctic Ocean or somewhere off in far northern Canada. There may not be many weather stations that can capture what this pressure system is doing at that point in time and then be able to forecast exactly how it will mature in 48 hours or 60 hours. So there's often some challenges when we have weather systems coming from those different directions compared to weather systems coming from the off through the Bering Sea. Even though I say that, though, there are some times when the computer models, even with a system moving northeast over the Bering Sea, have some differences, and it depends on what's happening further upstream, like way south of Kamchatka over Japan or China or wherever, that can influence how the computer models will behave later on.
There's another, I know I said Chinook. How about the Siberian train? When I was living on the west coast, they talk about the Siberian train or weather coming in from Siberia. Is that, are we looking at pressure systems in that case, or is that just the wind, a common
Well,
thing?
are you talking about a change in weather like for colder or windier or both or
Colder?
yeah. That is typically a high pressure system that formed over the Russian Arctic or the northern part of Russia. Has a lot of cold air with it. And the atmospheric flow patterns at upper levels are starting to move that pressure system so that it's moving now. It's expected to move over the Chukchi Sea and then down into the northern part of Alaska. That will help. And of course, northern or Alaska, the mainland Alaska in the wintertime is all dark and white, so cold air masses can just get colder once they move in. So that is probably the scenario that was associated with what you're talking about.
One last question, and we like to thank all of you, the classes and villages that joined us today. But is it the pressure? Is it the birds heading south? Are they looking for a pressure system to fly up to and head out jet stream, or is that merely homing in?
I haven't studied much about bird migrations and pressure systems, so you may have to discuss that with someone more involved in bird migrations than myself.
Well, on that note, we'd like to thank you all for joining us today, and we look forward to seeing you again for our next lecture coming in February. We'll contact you. And like John Lingus, we appreciate the learning we've had on the pressure system, and thank you again.